Okay, so what does it mean when you have an absorbing Markov chain? Well, let's consider a given matrix right here. We're given a transition of probability matrix, and each column designates each column and row designates a state where we have S of 1, S of 2, S of 3, and as many states as there are. And from here, pertaining to our matrix, each column and row is its own state. And in order for the state to become an absorbing state, in the matrix of transition probabilities, P, or the entry within the matrix, has to be 1, which is identified right here. That is, the entry of the main diagonal of P is 1, and all other entries within that column of P are 0. Now, there are two properties for an absorbing Markov chain to occur. That is, if it has at least one absorbing state, and it's possible for it to move from a non-absorbing state to an absorbing state in a finite number of transitions. Let's begin with an example. Okay, so here's a Markov chain. Can we convert this to a matrix? So let's write down our P matrix. So we have P is equal to, well, let's acknowledge our states from S1, S2, S3. And then we're going to put in our states for the columns for S1, 2, and 3. Now we can begin writing the matrix. So from S1 to S1, we have 40%, which can be converted to 0.4. And from S1 to S2, we have 0%. There's, well, visually you can see that. So there we go. From S1 to S3, we have 60%, which is 0.6. Go ahead and pause the video, finish the matrix, and I'm going to cut to the final matrix, and let's see if we got the same thing. Okay, so this should be your matrix. Is it stochastic? It better be. And let's see here. We established that in a matrix of finite number of transitions, the entry within the P matrix should have a 1 with zeros surrounding it. So which column or which state would be the absorbing one? And if you said it was S of 2, you would be correct. On top of that, the corresponding Markov chain is also absorbing because it's possible to move from S1 to S2 in 2 transitions. And it's possible to move from S3 to S2 in 1 transition, as depicted in the following illustration to the left. So let's consider the following Markov chain. As you can see, we have 2 states. We have 2 pairs of states interacting with each other, so this is going to make things a little interesting. However, we can still devise the P matrix. So, how do we begin? Well, let's start off with the notation as P equals from, well, we have 4 different states, so that means we should have well, what would the dimension of the matrix be? Well, it should be S of 1, S of 2, S of 3, and SF4, and the same applies to the columns as well. Okay. So let's see here. From SF1 to SF1, we have 50%, and from SF1 to SF2, we also have 50%. So we have 0.5 and 0.5. Now from SF1 to SF3 and SF4, there's no transitioning for either or, so we can just denote that as 0. Then go ahead and pause the video and fill out the matrix yourself, because you're going to be repeating the same step. So this should be what your matrix, this should be your matrix right here. And now, where is our absorbing state? And if you were to assert that the second state is absorbing, you would be correct. However, the corresponding Markov chain isn't absorbing. Do you know why? Well, let's look at the diagram right here. Is there a way for SF3, the third state, or the first state to transition to the second state? Well, no, based on the picture. And as a result, the entire chain isn't necessarily absorbing, but the second state is. Okay, so let's say we have this Markov chain. I know it's a little messy, but let's just focus on one state at a time. So we know there are four states. So what does that mean? Well, our matrix is going to be 4 by 4. So let's write that down. Okay, and now let's look at the first state. From SF1 to SF1, we have 50%. So we have 0.5. However, from the second state, what about from the first state to the second state? Well, based on the picture, we have 20%, so that's 0.2. And from the first state to the third state, we have 10%, so that's 0.1. And from the first state to the fourth state, we have 20%, so that's going to be 0.2. So pause the video and repeat this process for the remaining states. So this is what your matrix should look like. And how many absorbing states are there? Keyword, it's states, plural, so there's multiple in this Markov chain. And if you were to say it was the second and fourth state, you would be correct. I'd also like to add something. So the corresponding matrix, is it absorbing or is it not absorbing? Well, it turns out, based on the Markov matrix, it is possible to move from either of the non-absorbing states, which is the first or third state, to either of the absorbing states in one step. And as a result, because you can move from non-absorbing to absorbing, the Markov chain is therefore absorbing. And that's it. I hope I made this clear. If you guys are still confused, I will post a follow-up video for you specifically and maybe others who are in the same boat. But feel free to like, comment, subscribe, and I look forward to posting more.